Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 8 on Asymptotics. In this lecture, we're going to take a trip to Asymptopia. Asymptopia is a land where we have an infinite amount of data, so it should be fun. We're going to talk about limits, but limits of random variables. And so there's intricacies that you have to account for when you consider random variables instead of standard mathematical limits. And it's a quite difficult subject, but we're going to show that we have basically two tools, the law of large numbers and the central limit theorem, that are going to be our primary methods for looking at limits of random variables. So let me just review numerical limits first. And I'm not going to go into too much detail, and I'm going to kind of treat it heuristically. Just to illustrate, in case your asymptotics is a little bit rusty, suppose I had a sequence where A1 was 0.9, A2 was 0.99, and A3 was 0.999, and I hope you can get the pattern at this point. So clearly this sequence, in some sense of the word, converges to 1. It converges to 0.9999999. So that gets closer and closer to 1 as the element of the sequence gets larger and larger. Well, we can formalize this. The formal definition of a limit is for any fixed distance, we can find a point in the sequence so that the sequence is closer to the limit than the distance from that point on. So take, for example, this sequence. The distance between an and 1 is 10 to the minus n, where n is the point in the sequence. And so if we pick any distance, say epsilon, we can find an n so that 10 to the minus n is smaller than epsilon, and then because 10 to the minus n just keeps getting smaller as n gets larger, then it's smaller than epsilon from that point onward. So that satisfies our definition of a limit, so clearly this converges to 1. And it's kind of an interesting fact that an infinite sequence of 0.9s and 1 is the same number. But that's kind of an interesting fact that if you ever take a class on real analysis, they'll discuss that sort of thing at length. But anyway, I hope you get this basic sense of a limit. As n goes to infinity, the sequence converges or looks more and more like its limit so that the distance just gets closer and closer and closer and never gets bigger again. The problem with that is that that only works for just a series of numbers, right? Now we want to talk about, say, limits of averages of coin flips. And then it gets much harder. So take, for example, the average. And now we're going to talk about an average comprised of n observations. So let's say xn bar, and now instead of saying x bar like we typically do, which is our average, we're going to annotate it by a subscript n to show that it's an average of the first n of a collection of IID observations. So for example, x bar could be the average of the result of n coin flips, which is the sample proportion of heads. Well, there is a limit theorem for averages, and we would say that xn bar converges in probability to a limit, and we relate this back to the ordinary definition of limit by saying, well, the probability that x is closer than any specific distance converges to 1. So in this case, probability xn bar minus the limit being less than any quantity epsilon that you fix, then that probability is a number, Pn, right? And the definition of convergence in probability is that sequence of numbers, Pn, converges to 1, right? So we've converted the problem of what does it mean for a random variable to converge, we've converted that back to the definition of convergence of a series of numbers. We've said convergence in probability implies a convergence of the collection of probability numbers in the standard sense of the definition of convergence. So now we have a way of talking about how random variables converge. So establishing that a random sequence of variables actually converges is hard. As you can imagine, it's hard. If you look back at the previous definition, it's not the easiest thing in the world to think about. So we have something that makes it a lot easier for us, and that's called the law of large numbers. So if you've heard people talk about the law of averages, typically they don't know what they're talking about, but probably they're referring to the law of large numbers. And the law of averages, or the law of large numbers, basically says that If xn to x1 are IID from a population with mean mu and variance sigma squared, so in this case, we're going to assume that the random variables have a variance. It's interesting to note that there are distributions where there is no variance. You try and calculate the variance and you get infinity or something like that. In this case, we're going to assume that there is a variance and that it's finite. Then the sample average of IID observations always converges in probability to mu. And that's called the law of large numbers. Probabilists make a lot of distinction over various kinds of the laws of large numbers, and they've worked very, very hard to get kind of minimal assumptions for the law of large numbers to work. And in fact, we're using a very lazy version of the law of large numbers. They would probably be upset at us for teaching this one, but it's okay. We don't care. The basic idea I want you to get is that averages converge to mu. Averages of IID observations converge to mu, the population mean that from which the observations were drawn. This is a good thing, right? This basically says if we go to the trouble of collecting an infinite amount of data, then we get the number that we want to estimate, mu, exactly, right? Which is good because collecting an infinite amount of data takes a lot of time, actually an infinite amount of time. If you're willing to make this many assumptions, the x's all have a finite variance, it's pretty easy to prove the law of large numbers using Chebyshev's inequality, which Chebyshev's inequality, if you remember, had a pretty simple little proof. So this kind of very complicated idea, it's amazing that it has a fairly simple little proof. So remember that Chebyshev's inequality states that the probability that a random variable is more than k standard deviations from the mean is less than 1 over k squared. So therefore, the probability that xn bar minus mu in absolute value is bigger than or equal to k standard deviation of x bar sub n is less than or equal to 1 over k squared. Now, let's pick an epsilon. Pick any distance epsilon, because remember, to establish the convergence of a limit of numbers, we have to pick an epsilon. And now to establish convergence in probability, we have to show that the probability that xn bar minus mu being bigger than epsilon goes to 0, or being less than epsilon goes to 1. Those two statements are equivalent. And so let's let k from our previous definition be epsilon divided by standard deviation of xn bar. K is not a random variable, right? Epsilon is a number that we pick, and standard deviation of xn bar is a random variable, but the standard deviation of it is sigma over square root n, okay? So this is just a number. There's nothing random in our definition of k. So if you plug that back in for k, right, you get the probability that xn bar minus mu being bigger than epsilon is less than or equal to the standard deviation of xn bar squared, which is the variance of xn bar, divided by epsilon squared. And we, from a previous lecture, already calculated what the variance of xn bar is. It's sigma squared over n. So this probability is less than or equal to sigma squared over n epsilon squared. Now, as n goes to infinity, sigma squared isn't changing and epsilon squared isn't changing, and the n's in the denominator, so this whole thing goes to 0. Okay, so the probability that the random average xn bar is more than epsilon away from the mean goes to 0 as n goes to infinity, or restated, the probability that xn bar is less than epsilon from the mean goes to 1 as n goes to infinity. So in either of those statements equivalently say that xn bar converges in probability to mu. I think it's kind of staggering that it's really basically 2 lines is all you need to establish this fairly complicated result. Now on the next page, I just have a simple example where I simulated random normals with a mean of 0, and I show the cumulative sample mean. So I took one random normal, and then I took that random normal and generated a second random normal, and then averaged it, and then generated a third random normal, and just averaged it with the remainder. And the iteration on the bottom is the number of observations that goes into that mean, right? And then on the vertical axis, it shows the value of the average. And you can see at first there's quite a bit of variability, right? Remember, the variance of the average is sigma squared over n, so the variability is going to 0, and this dashed line is the asymptote, right? And as you can see, this average, as we include more observations in it, is going to converge to this. You can see it already converging a little bit by 100 iterations to this dashed line. That's simply the law of large numbers. So let's cover some useful facts about the law of large numbers. One interesting fact is functions of convergent random sequences converge to the function evaluated at the limit. So this includes sums, products, differences. So for example, xm bar squared converges to mu squared, right? Because x bar converges to mu, and so this is just a function of x bar, so xn bar squared converges to mu squared. Something different is that average of the squared observations converges to a different entity, okay, right? Let's go through this a little bit carefully just because it's kind of an odd little point. So xm bar squared converges to mu squared, but if we sum up xi squared, the individual observation squared, and divide it by n, that no longer converges to mu squared. Well, why not? Well, it's the difference between the square of the average and the average of the squares. So in this case, it's the average of the squares. In this case, each xi squared is a random variable. So we could just call it y instead of xi squared. And then their average of these xi squareds, or average of these y's, is going to converge to the population mean of those y's. Well, we can calculate that. We know what the expected value of xi squared is because we can use the shortcut formula for the variance, which recall was expected value of xi squared minus expected value of xi quantity squared. We can just work that formula to solve for expected value of xi squared and show that that's equal to sigma squared plus mu squared. So the average of the squared observations converges to sigma squared plus mu squared, whereas the square of the average converges to mu squared. So it's kind of an interesting little point, but just remember that those things are different. And by the way, this little fact that we just showed, we can use this to prove that the sample variance converges to sigma squared. And we'll do that on the next slide. So let's actually go through this proof that the sample average converges to sigma squared. And I think you'll see in the process of the proof that it doesn't matter whether we divide by n or n minus 1, it's going to converge to sigma squared. So here we have the definition of the sample average. Summation xi minus xm bar squared, all divided by n minus 1. We're going to use the unbiased estimate of the sample variance. Well, recall there was a shortcut formula for the sample variance, and it worked out to then be the numerator had a shortcut formula that was summation xi squared minus n x bar squared. And so we're going to use that formula, and then we get summation xi squared over n minus 1 minus n bar squared over n minus 1. And let's just rearrange terms and multiply and divide by some n's because that n minus 1 is a little annoying. So we have n over n minus 1 times summation xi squared over n minus n over n minus 1 times xm bar squared. Well, let's look at each of these things in turn. And remember, from the previous slide, I told you, I didn't prove this and just have to take it as true, is that, if you multiply convergent sequences, they converge to the product of the limits. If you add and subtract convergent sequences, they converge to the difference of the limits and so on. So let's look at each of these terms one at a time. N over n minus 1, clearly that converges to 1. If you don't believe me, plug n over n minus 1 in for a very big value of n in your computer, and you'll see that it gets closer and closer to 1. Probably the easiest way to see this is it's 1 over 1 minus 1 over n, and that 1 over n clearly goes to 0. Okay, we just on the previous slide talked about how summation xi squared over n converges to sigma squared plus mu squared. So the second term converges to sigma squared plus mu squared. Then we have minus n over n minus 1, which again converges to 1. And then xm bar squared converges to mu squared. We talked about that on the previous slide. So we have this expression right here, sigma squared plus mu squared minus mu squared, which is just sigma squared. So that proves that the sample variance converges to sigma squared. And then, of course, the sample variance, if we happen to divide by the biased sample variance, if we happen to divide by n instead of n minus 1, also converges to sigma squared. And then we can square root the sample variance and get the sample standard deviation and see that it converges to sigma as well, just by the rule from the previous page where we said that functions, in this case the square root function of convergent random variables, converge to the function of the limit. So what we've found is we have our law of large numbers, and with a couple of rules that we just stipulated, we've got that the sample mean of IID random variables converges to the population mean that it's trying to estimate. The sample variance converges to the population variance that it's trying to estimate. The sample standard deviation converges to the population standard deviation that it's trying to estimate. And in all these cases, you see the pattern that the sample entity converges to the population quantity that it's trying to estimate, basically saying that if you go to the trouble of collecting an infinite amount of data, then you actually get the value that you want to estimate. You don't get it with noise, you get the actual value. We give this name a property, and we say that an estimator is consistent if it converges to what you want to estimate. And the law of large numbers is basically saying that the sample mean is consistent. And then we now know that the sample variance and the sample standard deviation are consistent, and it doesn't matter whether you're dividing by n or n-1, they're all consistent. But also remember that the sample mean and the sample variance are unbiased as well. And by the way, the sample standard deviation is not unbiased. Consistency, by the way, is a very weak property. So the sample standard deviation is biased, unlike the sample mean and the sample variance. Consistency is a very weak property. Saying that an estimator is consistent is not even really a necessary property. It seems like it should be necessary, but if something converges to mu plus epsilon, where epsilon is a minuscule number that is of no importance, then that estimator is not consistent. So it's fair to say that consistency is sort of a kind of a weakly necessary, but definitely not sufficient property for an estimator to be useful. We've also seen that being unbiased is neither necessary nor sufficient for an estimator to be useful either. For example, we talked about the bias variance trade-off, that estimators can be slightly biased, and you can want that because you improve on the variance. So what we're winding up with is a collection of properties that describe estimators, and you really need to think about the collection of properties as a whole to evaluate an estimator. And these various mathematical concepts are useful, but they never in isolation tell the full story on the utility of an estimator. They might be useful for eliminating really dumb things. If something's definitely not consistent in a way that it doesn't converge anywhere near the estimate, probably that's not something that you want to use. But apart from those kind of stark circumstances, these properties you need to take as a collection to try and decide which estimators are the right ones to use. So let me give an example of an estimator that's consistent but not very good. So take the data and only take the first half of the collected observations. So we have, instead of xn bar, we have xn over 2 bar, right? That estimator is, of course, consistent as n goes to infinity. It just has fewer observations than if you took all of them, but still the n is going to infinity. In this case, it's just n over 2. So that estimator is consistent, but it's got an obvious better estimator right in front of you, basically the estimator using all of the data. So there's a particular example of an estimator that's not consistent, where there's a better estimator that comes to mind. Here you have to actually account for the fact that the estimate with all of the data has a lower variance than the estimate with half of the data. So that's enough discussion of limits and the law of large numbers. Next, we're going to go on to the central limit theorem, a very important theorem in statistics. Hi, welcome back to this lecture on asymptotics. We're going to talk about the central limit theorem, one of the most important and celebrated theorems in statistics. The idea behind the central limit theorem is very neat. It gives you a way to perform inference with random variables. We actually don't know what distribution they come from. And basically what the CLT states is that the distribution of averages of IID variables, properly normalized, becomes that of a standard normal as the sample size increases. It's basically saying is if you want to evaluate error rates associated with averages, it's often enough to only compare them relative to a normal distribution. And the CLT applies in an endless variety of settings. And with a collection of various asymptotic tools, people have figured out a way to apply the central limit theorem in so many cases. the majority of inference you do, if you've used statistical software and calculated a p-value or a confidence interval, probably the underlying motivation of what you're doing is asymptotics in most cases. Maybe not all cases, but definitely not all cases. But in most cases, you're probably appealing to some use of the central limit theorem, especially if you have larger sample sizes. Let's actually just state the central limit theorem, at least as far as we're going to use it. So let's let x1 to xn be a collection of IID random variables. They come from some population with mean mu and variance sigma squared. And let's let xn bar be their sample average. Then probabilities, and in this case, let's look at the distribution function. The distribution function of the normalized mean, so we take xn bar, subtract off its expected value, mu, and divide by its standard deviation, sigma over square root n. So this whole quantity here has mean 0 and variance 1. So this probability that this z random variable is less than or equal to the specific point z is the standard limits to the standard normal distribution evaluated at that point z. Okay, so what does this say? This basically says that probabilities associated with sample means look like probabilities associated with normals. And if you standardize the sample mean so that it has mean 0 and variance 1, then the probabilities look like standard normal probabilities. So I wanted to reiterate the form of this normalized quantity here. It's xm bar, an estimate, minus the population mean of the estimate divided by the standard error. Okay? And this is something that you can practically bank on, is if you take any statistical estimate based on IID data and subtract off its population mean and divide by its standard error, that quantity is most likely going to wind up limiting to having a standard normal distribution. Let's just go through an example. And this is kind of a neat example, and I'll explain why in a minute. Imagine if you were stuck on a desert island. And bear with me. Imagine if you needed a standard normal random variable. You had to generate a standard normal random variable because you were kind of going crazy. And all you had was a die. So you were thinking, I need a standard normal random variable, and I have a die. Let's roll the die a bunch of times and then take the standardized sample mean and see how well that works as a standard normal by applying the central limit theorem. So remember that for a die, the expected value of a die roll is 3.5. If you don't remember, we went through this calculation a couple lectures ago when we covered the variance. The variance of a die roll is 2.92. And the standard error is square root 2.92 divided by the number of die rolls going into the average. So that's 1.71 divided by square root n. And so the standardized mean would just be the average of the die rolls minus 3.5 divided by 1.71 divided by square root n. On the next slide, basically what I've done is I rolled the die, let's say one time, and I did that over and over and over again, so an average of 1, and I standardized the average of 1, right? So in this case, for an average of 1, it would be a die roll minus 3.5 divided by 1.71. So now we have a distribution that's centered at 0 and has variance 1. And I plotted the standard normal density in gray in the back, and I plotted the histogram of my die rolls. And of course, it can only take 6 possible values, and you see those 6 spikes at 1 to 6. And it's not perfectly discrete because the software I'm using to plot the histogram assumes the data is continuous. So you see the 6 spikes basically from the fact that one die roll, if we plot a histogram of a bunch of 1 die rolls, they're going to look like a bunch of spikes at 1 to 6. And in this case, because it was normalized, they're going to look like the numbers 1 to 6, where you subtract off 3.5 and divide by 1.71. Okay, now imagine if I just took 2 die rolls. I took a die, I rolled it once, I rolled it a second time, I got my average, I subtracted off 3.5, and I divided by 1.71 divided by square root 2. And I repeated that process over and over and over again, and I plotted a histogram of the result of a lot of averages of 2 die rolls. And so the histogram is going to give me a good sense of what the distribution of the average of 2 die rolls is, the standardized average of 2 die rolls is. And in the background, we have the normal distribution, and on top of it, we have the distribution of the average of 2 die rolls. And I think you'll agree that it's already, just by 2 die rolls, looking pretty good. amazingly good. And now imagine if you had 6 die rolls. So I rolled the dice 6 times, right? Took the average, subtracted 3.5, and then divided by 1.71 divided by square root 6, right? And then I did that process over and over and over again, and I got lots of normalized averages of 6 die rolls, and I plotted a histogram, and you can't even see the standard normal distribution in the background because the distribution of the average of 6 die rolls looks so similar. So if I was on my desert island and if I needed a standard normal, I think I could probably get away with 6 die rolls and taking an average, subtracting by 3.5 and dividing by 1.71 divided by square root 6. And the reason why I bring this up is because it's an interesting fact. The famous statistician Francis Galton, who was quite a character, you should look up Francis Galton if you get a chance. He was Charles Darwin's cousin. And he's a very brilliant guy. He needed standard normals, but he was trying to get to simulate standard normals prior to having computers. So how did he do it? Well, he basically rolled dice and applied the central limit theorem to get standard normals, which is really quite clever. And he had, because it was a pain in the butt, and he wasn't on a desert island, so he had time constraints, he actually invented dice that made it a little bit easier for him to do. I think he took standard dice and kind of wrote on the corners and stuff like that, so there was more values than 1 to 6. But the basic idea is that the distribution of averages looks like that of a normal distribution. And with kind of just about in any sense, regardless of what the underlying distribution of the data is. There's some assumptions there. We assume that the variance was finite and some other things like that. But for the purpose of this class, it's basically any distribution that we can probably think of. So let's take another version of the central limit theorem, or another instance of the central limit theorem from flipping coins. So now instead of a die, I have a coin and I want to evaluate the average of a bunch of coin flips. So let's let xi be 0 or 1 result of the ith coin flip of a possibly unfair coin where the p is the true success probability of the coin. And the sample proportion, say p hat, is just the average of the coin flips, right? The p hat is, in this case, the percentage of ones, and the average of the xi is the same thing, of course. So remember that the expected value of the xi's is p, right? The true success probability of the coin. And the variance of the xi's works out to be p times 1 minus p. And then the standard error of the mean in this case is the variance divided by square root n. So it's p times 1 minus p divided by n square root the whole thing. So then what this says is that if we take a sample proportion, p hat, we subtract off the population proportion, the success probability, the probability of getting ahead, and divided by square root p times 1 minus p divided by n, that'll be approximately normally distributed. And things look worse than the die roll in this case. Let's take a fair coin and generate some plots. So if you take a fair coin and flip the coin and record either 0 or 1, depending on whether it's heads or tails, subtract off 0.5, and divide by square root 0.5 times 1 minus 0.5, and do that over and over again and get a histogram of the results. You only get 2 possible values, right? They're not 0 or 1 because you've normalized them. And here in this first plot, you see it doesn't look normal at all, of course. After 10 coin flips, so here now we're flipping the coin 10 times, taking the sample proportion of heads, subtracting off 0.5, and then dividing by 0.5 times 1 minus 0.5 divided by 10, square root of that whole thing. And we repeat that process over and over and over again and get a histogram of the results. We see that the distribution of the normalized average of 10 coin flips looks pretty normally distributed, but still it's very discrete compared to the normal distribution. Once you get to 20 coin flips, it's looking pretty good. It's overlaying the standard normal distribution pretty well. And it turns out in the coin flipping example, it converges to normality quick if the coin is fair. If the coin is unfair, if you see the bottom row of plots, here we have a coin that's unfair where it's more likely to get a tail than a head. I think it's 0.7, 0.3, I believe is what I used for the simulation. Then you see that, at the start, it's much more likely to get the 0 value than the head value, the 1 value. These aren't 0 and 1 because they've been normalized. If you look at the distribution of averages of 10 coin flips, it doesn't look very normal at all. 20 coin flips, it still doesn't look very normal. So it takes a lot longer. So this is a problem with the central limit theorem that generally doesn't get a lot of play. The central limit theorem says basically if you have IID random variables and you take an average, the distribution of the normalized average converges to that of a Gaussian distribution. But it doesn't tell you how fast it does that, right? It just tells you that it does eventually. So for some distributions, it might take thousands of observations going into the sample mean for the distribution of sample means to behave like that of a Gaussian distribution. And for others, like the die roll, we saw that it only took 6, and then it was nearly overlaying the standard normal distribution. So, it's an unfortunate fact that the central limit theorem can't give you any guarantees on how quickly things converge to normality. Oh, and I wanted to point out one last thing on this coin flipping example. So if you've ever been to a science museum and you've seen these machines where, say, a ping pong ball is dropped and it goes through like kind of a pachinko collection of left-right decisions kind of randomly, that's exactly a binomial experiment. Every time the ping pong ball hits a nail, basically, it can either kind of with a 50% probability go left or right. And so by the end of the process, it's had a bunch of coin flips. And so the position it is at the bottom is exactly the sum of a bunch of Bernoulli trials in principle. You have to actually create it so that it approximates the coin flipping well. For example, if it was tilted to the side, it wouldn't be a fair coin anymore. But as it gets towards the bottom where the ping pong balls are collected, it's a sum of a bunch of Bernoulli random variables. Well, the distribution of averages is approximately Gaussian, so of course the distribution of sums is then approximately Gaussian because sums are just averages multiplied by n. So what you'll see in the Science Museum is that in the bottom they'll have traced out a Gaussian distribution, and you'll see that if they run this ping pong ball machine long enough, the balls tend to fall in a bell-shaped curve. And that's just an application of the central limit theorem saying that for this particular value of n, the central limit theorem approximation of the sum of a bunch of coin flips is pretty good. And this ping pong ball device is actually called a quincunx, and it was invented by Francis Galton, who we talked about earlier, the cousin of Charles Darwin. So it's kind of a very interesting little tidbit. So the next time you're at the Science Museum, you can explain this to whoever you're with. So the reason we use the central limit theorem in practice, it's useful as an approximation, basically saying that the normalized mean, it has a distribution that's approximately like the standard normal distribution. So let me give you an example. So remember that 1.96 is a good approximation to the 0.975th quantile of a standard normal. And so negative 1.96 is a pretty good approximation to the 2.5th percentile. So what the central limit theorem then says is that 95% is about the probability that a standardized mean lies between basically -2 and +2. So let me just repeat that. So it's about 95% the probability that a standardized mean lies between the values -2 and +2. And then so let's take the interior of this probability statement and just rearrange terms a little bit, making sure that if we multiply everything by a minus sign, we flip the inequalities. And we get that xm bar plus 1.96 sigma over square root n is bigger than or equal to mu, which is greater than or equal to xm bar minus 1.96 sigma over square root n. That probability is about 0.95. What that's saying is that the random interval xm bar plus or minus 2 standard errors contains mu, the non-random entity, with about 95% probability. Let me give you another formula that I find super useful, a super useful instance of the CLT because it's a kind of quick back of the envelope type calculation. So by the way, we're going to spend much more time calculating specific confidence intervals and so on. Right now, we just wanted to give you the theory behind why confidence intervals work. But there's a specific instance of confidence intervals that's really quite useful. So for sample proportions, remember the variance is p times 1 minus p. And so the confidence interval, just plugging in, takes the form p hat, the sample proportion, plus or minus the standard normal quantile, times square root p times 1 minus p over n. Now, in all of the intervals, p is what we want to estimate, so we obviously can't plug into this formula. We need to replace p with an estimate. If we replace p with the sample proportion, p hat, 1 minus p hat, you get a so-called walled interval. And as I stated in this previous slide but didn't really talk about, you generally replacing the unknown parameters in the standard error calculation with their estimates will usually work with something that's called Slutsky's theorem. And that will usually work and will create an interval that's asymptotically valid. Let's try and, instead of doing that right now, we'll talk a lot more about walled intervals and that sort of thing. Let's actually talk right now about quick back of the envelope bounds. So remember that the worst that p times 1 minus p can be, the biggest it can be, is if p is a half. So this thing is less than or equal to a quarter, as long as p is between 0 and 1, which is our restrictions because we're talking about a proportion or a probability. So in this case, if we let alpha be 0.05 so that the standard normal quantile is 1.96, which is close enough to 2, among friends, let's just call it 2, then the standard error, the whole kind of margin of error part of the confidence interval, 2 square root p 1 minus p over n, works out to be 2 times square root a quarter divided by n, and so you wind up with 1 over square root n. So if you want a quick back of the envelope confidence interval estimate for a sample proportion, just take the sample proportion and add and subtract 1 over square root n, and that's a really handy little formula. And it kind of tells you sort of when you calculate a proportion about how accurate it is. So for example, if I have a proportion of 100 coin flips, we know that the accuracy is going to be about 1 over square root 100 or 0.1. So it's a very useful little back of the envelope calculation. Just remember p hat plus or minus 1 over square root n. Well, that's the end of today's lecture on asymptopia. I hope you enjoyed your visit to Asymptopia. It's a very nice place. When you have an infinite amount of data, things tend to work out. I look forward to seeing you next time.